We are going to start a talk from Al and Arnie. One Packer to rule them all, empirical identification, comparison, and circumvention of current antivirus detection techniques.
Hi. Good morning, I'm Arne. Next to me is Aladdin, and today we're just going to talk about our research regarding antivirus detection and circumvention techniques with a dedicated tool called Packer. So the agenda for today is limited, as is our time slot. First of all, I will introduce the term packing for those who are unfamiliar with it yet. And hereafter, we'll be covering the three main detection techniques that we've identified in antivirus products. First of all, I will be covering the static detection we all probably know of. And hereafter, Aladdin will cover the code emulation and dynamic detection techniques. Brief introduction about us. We are, as you've noticed, we are not American. We are both from Europe. I'm from Belgium, and Aladdin is based in France. And we are penetration testers in our day-to-day job. So, packing. Packing is actually the transformation of an executable into another executable, which exhibits the same or even enhanced functionality, but has a different file system footprint. And a good example of a packer is, for example, a compressor like UPX, which compresses a file and then also appends a piece of code called a stub to the final executable, which will undo the compression. So the stub, it's injected into the final executable, and it will decompress before handing over execution to the original executable in memory. So with regard to static detection of antivirus companies, we can all see why a packer could be useful, because a packer can change the footprint and the signature of a file on disk. And of course, since antivirus companies are using signatures to statically detect malware, it is obvious that a packer is useful to do proper circumvention. Of course, antivirus products also know that malware authors are actively using packers to make their malware undetectable again. So antivirus products are really also trying to detect modifications that a packer makes to an executable in order to see if it's suspicious or not. To understand how a good packer can be made, we first have to take a brief look into the portable executable file format of Windows. Of course, our research was focused on Microsoft executables because this is the platform where malware is mainly at stake. So if we look into an executable, it has two general categories or sections. So the first one is the header, which contains really only metadata, which is used by the operating system to load your executable in memory and execute it properly. And hereafter, you have a data blob, which is logically divided into sections. So in the header, you have a number of fields, like the address of entry point, which points to the first instruction in the data sections where execution should be started. And the header also contains a section table which logically divides this data into sections. So a quick example, a program example is the following. We have a simple C program which calls a message box saying hello world. And if you look into the section table of this program, we can see there are 5 sections. The first one is a text section, which actually contains the assembly code of your program, which is generated by your compiler. And this text section actually contains absolute references to the next 2 sections, which are the RData, or also called the import section, and the data section. The data section contains the static strings or the static data from your program, for example, the hello world strings. The RData section is the imports section of your program, and this actually contains at runtime the addresses of the Windows API functions that the program is counting on. So in this case, message box. Of course, at static on disk, this address is not present in this section because the function addresses of Windows APIs, they differ between operating systems and even service packs. So actually on disk, this imports section contains a structure which informs the Windows operating system which addresses are required by this program. And at loading time, the Windows PE loader will then hot patch the addresses of these functions in memory in this section. But what is really relevant for a packer is that the text section contains absolute references to the 2 sections below it. And for this reason, the text section cannot be easily extended. So because you would move the section below it to another virtual memory address, and you would break these absolute references. So this is one of the main limitations for a packer. A second limitation is also that the import section contains a data structure which is required to be valid statically. So the Windows operating system loader will read and parse these structures before really running the executable. And this is also the same for the two latest sections, which are the resource and the relocation table, resource and relocation section, which are actually, they also contain data structures to relocate an executable in memory when ASLR is enabled. And for example, the icons of an executable are present in the resource section. So when building a packer, you have two main challenges. The first challenge is you need to create a stub which you can inject into the final executable. This stub is actually should be assembly code because we're working with low-level executables here. And assembly code is architecture specific. Second of all, requirement is that the code is position independent and self-dependent because you cannot count on the Windows operating system to hot patch, for example, the addresses of your required Windows API functions of your stub, and thus you need to deal with it yourself. So we've come up with a solution which is called reflective DLL injection. Anyone knows the reflective DLL injection project? Anyone knows it not from Metasploit? Okay, cool. So this actually is an open source project from Stephen Fewer, which allows you to write C and C++ code, compile it to a DLL for 32-bit, 64-bit, and even ARM code. 32-6 and 64-bit ARM code. And actually, you compile it as a DLL. You can inject it into a process, and then you just execute a reflective loader, which is a function provided by the reflective DLL injection project. And this reflective loader will actually load your DLL dynamically. So it will relocate your complete DLL into the heap. It will parse through the imports table. It will hot patch the Windows API functions that are required. And then it will hand over execution to the DLL main function, which has been implemented by us, which is actually containing our stub. Second main challenge of making a packer which can defeat static antivirus detection is we have to inject our stub in a way that it's stealthy, because antivirus products are really trying to detect the injection of stubs and generally modifications of packers. So we need to come up with a solution, but as I've told you before, there are some limitations because of the Windows PE file format. So what we've done first is we've looked at how other packers do it. Here's a brief summary of the section tables of the Hello World example that I've shown you before. And you can see that every packer actually mangles the section table a lot. So none of the section tables here is still legitimate or looks legitimate. So actually we didn't find a straightforward solution that we could simply copy there. So we've developed our own techniques. First of all, we've implemented a simple packing technique, which we called inline packer. And what we do here, on the left we have the input executable that we want to pack, and on the right we have the final generated executable by this packing technique. What the packer will do statically is we will encrypt the code and the data section in line, and we will append our stub as a new section. So appending a stub as a new section is a good option because you will not break anything. Appending a new section will not break like the addresses of the other sections. And when executing the stub will simply decrypt the code and data section in memory and then hand over execution to the original entry point in the code section. Now, we've done some tests with it packer on a number of malware samples for both 32-bit and 64-bit. And we've seen that, first of all, we've used a stub that does not completely decrypt the original executable, but actually we've used a stub that immediately calls exit process. So in order to really isolate for static antivirus detection, if you don't do it, code emulation hits, or some antiviruses perform also code emulation. So this is really to isolate the static antivirus detection. And what we see here is that for 64-bit, by packing just with a simple packer, we can see that only 2 antiviruses are still detecting our initial malware. For 32-bit, the story is a bit different. Some antiviruses are already completely bypassed, as you can see on the right. But for example, Qihoo antivirus, the Chinese antivirus solution that we've put in scope, it detected more malware samples that we packed with this technique than initially. So actually, this antivirus product is really detecting our packing technique rather than the initial malware. We thought about what the actual reason was that the antivirus products were still detecting a significant number of our initial malware, and we've identified the two major reasons. So first of all, we are injecting a stub at the end of the executable, and it's really obvious that this is not normal, because a normal compiler would not add a new section called stub at the end of the executable. Also, the entry point of our final executable is pointing to this last section, and this is also not normal behavior, because the entry point is usually always pointing to the code section, which is always the first section in an executable. Second of all, we are only encrypting the code and the data sections, because the other three sections are used by the Windows PE loader and must contain legitimate data on disk. And of course, the coverage of the packer is not complete because we are not encrypting all the sections. So we've come up with a solution. On the left, again, the initial executable. On the right, it's not a modified executable, but it's actually a completely new executable that we've based on both a template exe file and a exe file we want to pack. So first of all, what do we do statically? We take all the sections of the initial executable, we encrypt them, we append our stub to it, and this whole data blob, we make this our new code section in our final executable. So in this case, our stub is in the code section. We can point the entry point into our code section, and it's not suspicious anymore. Hereafter, we use the template file to borrow their legitimate sections, their legitimate data import table and resource sections, in order to let the final executable look legitimate. But of course, these are just for the view. It's not that they are really required to properly execute the final executable. So the stub has to do a little bit more work, because we need to resolve the import table from the packed executable ourselves. But of course, the reflective DLL loader can do it, so we can do it too. And when we tested this technique on the same malware samples, we've seen that it is really effective against 64-bit. None of the antivirus products are still detecting 64-bit malware samples packed with this technique. But for 32-bit, there are still 3 antiviruses who are detecting it. So we wondered, okay, what could be the reason? Because we solved all the previous issues. But what we came up with is our code section is actually containing encrypted data and a piece of code, which is called our stub. But this encrypted data, of course, the entropy of this section is not as a normal code section. So we think this is the reason that these antivirus products detect a subset of our malware packed with this technique. So we come up with a third one, which we designated the resource packer. And with this packer, we completely encrypt the original executable. We add a resource to a real legitimate template file, for example, a Windows file notepad or something. We overwrite a piece of the code of this template file with our stub. So the stub is in the code section of the final executable. And then we point the empty point to the reflective DLL loader in our stub. Dynamically, the stub will load the resource, decrypt it, overwrite the original codes and data sections of the executable, and then execute it. And now we see that this technique can evade all antivirus detection for both 32-bit and 64-bit. But as you remembered, I told you about the stub that we inserted an exit process call for these verifications, but when we remove it and we just again scan these files statically, we notice that 4 antivirus products were suddenly detecting the packed malware again. These were Microsoft, NOD32, Kaspersky, and AVG. And this is in fact the code emulation that I've referred to, and Aladdin will tell you more about it now.
Okay, well, hi everyone. Okay, so let's continue. So, as Arne has explained, using the resource packer, it's possible to bypass several antiviruses that use static analysis, except for a few that are using code emulation. So the question is it possible to bypass this detection method in a generic way? Well, first of all, the way antivirus emulators is being performed is that they are emulating the Windows environment in order to execute the malware inside the restricted box, trigger the unpacking in memory, and then do further analysis on it afterward. The problem, however, is that Windows environment is such a complex system that there are differences that exist between the emulated environment and the real environments. And it is these differences that we will try to exploit as attackers to perform initial checks that will decide on doing the unpacking that will trigger the antivirus detection. Well, to identify these differences and to evaluate the different emulators, we have worked on 4 categories. There are definitely more, but these are the ones that we did focus on. The first, which is related to timing anomaly. Second, which is network interaction, then file system interaction, and finally binary instrumentation. For the first category, these are actually checks that has already been documented as being used in the wild. And the principle is, because the antivirus cannot keep analyzing the malware indefinitely, malware author will try to stall the analysis by delaying the unpacking. And in this basic example, it is done by a simple big sleep. However, some antivirus emulators are able to bypass this evasion method by emulating the sleep function so that it will do sleep 1 or simply nothing. But again, malware authors adapt to this approach, and they will even try to detect this sort of behavior. And in this example, and the way they would do it is that they would use other EPA functions to say if the sleep function is working properly. In this example, it is done using the getTickCount function. But as you'll see afterward in our results, even some malware, some antivirus emulators are able to detect this kind of evasion methods or are able to bypass it. So we tried to come up with other checks that would allow us to detect this sort of behavior, but without the use of any EPA function. And the check we came up with is a check that uses 2 threads. There is one thread, which is the counter thread, and a second thread, which is the washer thread. And the counter thread is incrementing a shared variable separated by multiple sleeps. The watcher thread is verifying the counter variable after a big sleep. And in this example, the counter variable should be equal to 10. And this is what we should see inside a real environment. However, inside an emulated environment where the sleep has been reduced, what we will see is that the watcher thread will stop execution very early, and when it will try to compare it with the expected value, it will no longer match, thus allowing us to determine that we are running inside an emulated environment. And this is just an example of several of the timing checks that were implemented. There are more complex ones that you could check in the paper if you're interested in them. The second category, which is interaction with the network. And this is an example of a check that has been documented by a colleague called Jérôme Lequin, where he is using a connection on localhost to the SMB port to use as an indicator if we are running inside an emulator. The SMB port exists on all professional Windows operating system, and if the emulator fails to implement it, then we are able to detect the use of emulation. The third category, which is interaction with the file system. And here there are several checks that were implemented that verify the sanity of the emulator implementation, like reading and writing to files, to ADS streams, checking the timestamps of the created files. But there are also checks that were implemented that uses EPA functions that relies indirectly on the file system. And this is an example of a check that uses the load library function to load system DLLs and fake DLLs. If the system DLLs are not loading, this is not a fully functioning Windows operating system. And in the same fashion, if the fake DLLs are loading, we have just called the antivirus line to your own face. Okay. The final category, which is instrumentation, and this is based on work that has been done by 2 researchers, which are Francisco Falcon and Nahuel Riva, who came up with several checks to detect dynamic binary instrumentation. Few of these checks are very specific to the Intel Pen frameworks, but others are very generic. And this is an example of a check that will retrieve the parent processor name compared with cmd.exe and explorer.exe, which should be the case of our malware. If it doesn't match, then again, we are potentially running inside an emulated environment. Okay, well, this is a table that shows the result of a subset of our checks. This is a table that dates back from 1 week ago. We did the same checks back in March. We have already identified some notable differences. The most important one is that back in March, there are two antiviruses for which the resource packer was not triggering emulation. And it's the case of EVG and ESET antiviruses. And it's something that we could see because their implementation is less robust than the ones of Kaspersky and Microsoft. The second thing that we could see is that Kaspersky emulation is lacking when it comes to 64 bits. It's very comparable to Microsoft for 32-bit, and even in some cases superior to Microsoft, which is something that we wouldn't be expecting because Microsoft is emulating their own operating system, which is not the case of Kaspersky. The other notable difference is that we had checks that were allowing us to bypass emulation back in March, but which weren't working anymore, which is an indication that there is an active development of enhancing the evasiveness of the emulator implementations. However, as you could see, there are actually numerous checks that are able to bypass all the emulator implementation in a generic way, meaning that using the resource packer and one of these checks are able to bypass the initial analysis by all antiviruses. Well, however, and this is probably a problem that you have probably already faced before, is if, for instance, you have retrieved an interpreter shell, but when you try to perform certain action, it gets flagged by the antivirus and the process is killed. And to give you an example, if, for instance, you are on a machine with the EVG antivirus and you try to migrate to explorer.exe, it will be flagged by the antivirus. It will be unable to determine what kind of tool or malware it is. It will just say that there is something suspicious and kill the process and ask you to reboot the machine. So the question again was, is it possible to bypass this detection method in a generic way? Well, first we have to understand how this detection method, which is commonly referred to as dynamic analysis or heuristic analysis, is implemented. Well, some antiviruses, not all of them, some antiviruses uses a hooking technique called SSDT hooking. SSDT is a dispatch table that exists in kernel land that references functions accessible from user land. And by hooking the SSDT table, it's possible to log function calls with their different parameters in a way that it is impossible to bypass from a user land perspective. And this is used in the way that if the antivirus sees that there is a certain process, which is, for instance, calling function A followed by function B followed by function C with certain parameters, it will say, well, this is actually the signature for instance, process hurrying, which is mostly used by malware, and it will flag it as suspicious. Well, SSDT hooking is just one of the many hooking techniques that exist, and there is particularly one that we use to implement evasive techniques to bypass heuristic analysis, and it's a user-land in-memory hooking technique called inline hooking. What inline hooking does is, if for instance I'd like to hook a certain function, inline hooking will disassemble this function, it will replace the initial instructions with one that would allow us to jump to our newly allocated function, while making sure that it is correctly padded so that we can still use the rest of the instructions. It will also save these initial instructions to a new memory region called trampoline. However, it will also need to correct the trampoline. If, for instance, I have a relative jump, I'll need to correct the instructions so that I will still be able to jump to the correct address. And this is used to implement two evasive methods. First one is a method we call API translation. I know the name is bad. But the principle is, if for instance you'd like to perform persistence, you might be doing so by adding certain registry key, meaning you'll be using registry handling functions which might trigger a known signature. Well, instead of using this function, which will trigger known signature, API translation will transform them into a new call for which there is no known signature. And in this example, they are being replaced with a system command that we'll call the rig executable. And what will potentially happen is that the antivirus will see this coming from a different process, and this process is signed by Microsoft, so the profile risk is a lot lower, and it will no longer flag it as something suspicious. The second technique is a technique we call API junk injection. And the principle is, because antiviruses are expecting that there is certain function calls that are performed in certain order, by hooking these methods, these different calls, and by injecting function calls that do not modify the logic of the application, but modify the expected succession, we're able to no longer match the expected signature. The drawback, however, of this technique is that there is a significant performance impact. It's very generic to bypass a detection method that relies on this heuristic approach. However, there is a significant performance impact, opposed to the first technique, which has little or no impact on the application, but it's more difficult to implement because you'll need to come up with a heuristic, with an EPI translation for each heuristic signature, and it's not always that easy. In some cases, just not impossible. Okay, well, to rapidly summarize, what we have seen from our experiment is that there is an evolution of detection methods by antiviruses, either by simply enhancing their static-based capabilities or by the use of more powerful techniques. And it's, for instance, the case of code emulation, which we found it to be a very powerful method, but the problem is we believe that our feeling is that because implementing emulation is so difficult, there will always be differences that could be used as initial checks to try to bypass this sort of detection method. The second thing, which is the use of heuristic, and our experience trying to come up with generic ways to bypass this sort of detection method, it's that it's very difficult to implement generic ways to bypass it. The problem, however, is that heuristic analysis is only used after the executable has executed. However, we expect that the use of heuristic analysis is something that will gain momentum in the future, and we'll potentially see more robust use of it in the future. Okay, well, I hope that it was clear. If you have any questions, we'll be glad trying to answer them, and thank you for listening.